Good morning. Welcome to our first lab demonstration session here. We are here in Manufacturing Science Lab of IIT Kanpur, India. So here we have a setup in which we'll do grinding on titanium workpiece here. So we have already given the details, what are the workpiece specifications, what are wheel specifications, other things. So this workpiece has 25 mm of width and 160 mm length. So this will be machined with this our wheel, that is aluminum abrasive wheel. So we have various instruments here that would record certain responses which we'll use for our final optimization with respect to green parameters. So this is our aerosol air particle collector. This is a laser air particle collector. We have already just given some information on this one. So this will collect the data. It has 6 channels, 0.3, 0.5, 1.0, 5.0, 10 and 25 micrometer of particle size. So in this case, we have just recorded this ambient room aerosol, or what do you say, ambient room air particle size. So it has just brought up, given this specific rating here, 0.3 microns. These are the number of particles of 0.3 microns. And next we have 0.5 micron size particles. These are the numbers. So the smaller the particle size is, more will be the number of particles. So this is the total number of particles that we have obtained till now. Yeah. So this is one thing. This sound meter would record this sound, that is the peak and average sound that occurs during the machining. So see, the sound here coming is, this is a machining shop, the regular sound. It is of the order of 70. So when I speak, it reaches up to 86. So actually this is a workshop, so my volume is quite high. So it is coming 85 decibels here. So you can see the sound raised to even 107 decibels here. And in the room, as I already talked, that in the office kind of environment, so we have 55 decibel is the acceptable sound level. So this will record that in case the peak sounds, the peak inputs we receive here should be less than 10 per day. This is whatever recommended limit is there in the industry, specifically in India. So this is another instrument able to record sound. So these are for our green parameters, which we have chosen as green parameters. Okay, regarding energy, that is basically we in green, we think when we want to optimize with respect to energy, when we want to reduce the energy or minimize the energy input in machining specific this specific workpiece here. So this will be kind of a sample or an example experiment here. So energy would be recorded using this dynamometer. Right? This dynamometer will record the force that will further convert it to specific energy. This dynamometer is covered with actually the sheets, so as the aerosols and the other particles do not enter the machine and just have deteriorate machine components or workpiece, some other things, etc. So this will record it. This is connected with this cable to our control unit here. So this is our control unit. This is a LabVIEW software. So this is connected here. So in this case, the force is being transferred into electrical signal. That is 1 Newton of force is giving 1 volt energy. That is further calibrated. We have LabVIEW software here. So when we do machining, these are the force Fx. We have a force in X, Y and Z direction. In this case, Z is our normal force and Y is our tangential force. X direction we would not have any force here. So these two lines, which represent our Z and Y directions, would give us the normal and tangential forces. Tangential forces is mainly responsible for machining here. So that we'll use. So how to operate these things, how these things work, we'll just come up with that. So before starting experiments, we need to calibrate everything and make sure that we have the equipment so as there are no noise factors, not this sound noise, the other noise factors which externally affect, which cannot be controlled otherwise. So for that, this dynamometer is calibrated. So as we converted that 1 Newton to 1 volt, and some correction factors are put there in our LabVIEW software. And this wheel would be dressed, and everything, sound meter is like calibrated, and the aerosol collector, everything is cut. And the wheel meter is just will show how dressing is done here. So here we have a diamond dresser here, which is given 10 micrometer input, like feed here, and it would do machining. So we'll just see how the dressing done. This is Mr. Atul who will help us in that. You would start. See, he has already given 10 micron feed here. We call it feed. Actually, this is the like movement towards upside. And he is now bringing the wheel on this side. That is the transverse movement. So as the wheel is dressed. But this is like we will not run only one here. Like we not run it only once. There will be multiple runs. And this is recommended by the wheel manufacturer, the grinding wheel manufacturer. He recommends that these are the various parameters. Once he has done the dressing, now we are just touching this wheel with workpiece. So it is just in a contact. After that, we'll give some specific depth of cut and do machining. See, when he'll touch, we'll observe a spark here. Yeah, that means the wheel is touched here. Ready? Now what we have here is MQL setup. So this is why we are here, like this is the main thing we are doing, that we are just going to demonstrate how MQL machining is like conducted here. So in this we have this nozzle. Actually this nozzle is all fixed in our setup. Excuse me, let me show that. So we removed this attachment because we were to dress the machine, this wheel here. So this will again fixed. This nozzle is kept at 100 mm distance from our workpiece, like tool workpiece contact work point. And this is set up here. So this is a setup here. So we have already told you that this nozzle, this is a similar kind of nozzle here. This nozzle has air and liquid inputs here from the two walls, and we get the like mixture air atomizing here. So in this case, this is our round cap. The kind of spray would we have would be round, that we already discussed. So this is our round cap. We also have flat caps and some other things. So these are the 4 holes from which air would be coming, and there is an orifice from which liquid will be coming. So this is an external mixing kind of a nozzle. So in this case, I put this air cap here and lock it with my screw. I have a lock nut here, and the other body parts are already discussed, and it is already fixed here. So this has been calibrated so as we get streamlined flow, that so as machining is done like in a good way. So we have these pressure gauges, and this is the line which is giving air, right? And in this case we are having liquid, and we have used a separate setup here. What happens, it was observed that if we connect directly air and liquid here, this flow was not continuous, it was intermittent flow. Intermittent flow, that it will be coming flow like flow coming and stopping intermittently. So to counter that, we made an attachment, and we made this closed chamber. I put our fluid here, and these are pressure gauges, and air is pressurized to obtain. So this is the liquid going out towards the nozzle. So this air is like pressurizing this one, and the liquid and this air pressure towards the nozzle is controlled in such a way that we get continuous flow, right? Continuous like a spray here, right? So we'll fix this attachment and do machining. So what we see here in this air particle collector, this is Lazarus 2 model. I have just switched it on, and see it is giving 10 seconds of the initial rehabilitation time. The time like it just prepare to record. Then the recording starts here. So in every second, the pulse rate is 1 second here. In every second, it is recording some data here. So this data is then obtained in the like a pen drive or some other like way. We could even connect this directly to the computer, and that is used to find out the total like micrograms per meter cube of aerosols or air particles while doing machining. So we'll record the data, and this has been synchronized with our LabVIEW software as well, that when we record the data in the specific time when machining is happening. And then when the machining is happening, some aerosols would be like coming out, and the data recorded would obviously be high. So what are the specific data points, data like values coming, that we'll discuss. So when we stop it here, it will even print the average value of this time. It will even print this average value. Like in this time, in this specific time, it has for 59 seconds, it has recorded 0.3, 0.5, 1.05, 10 and 25 micrometer of particles, and these are the counts. Got it? Thank you. So we have now fixed this attachment here so as to keep this distance, specified distance where I just said. Now I have switched on the compressor, and it is giving, see, it is giving the spray here. The spray rate here is 100 milliliter per hour. In flood we have of the order of 5 liters per minute. This is 100 milliliter per hour. And see, the spray is also, the flow is also continuous. It is streamlined flow. It will specifically at the point, the workpiece, that like machining point here. So these instruments, these actually I am just a kind of makeshift kind of arrangement here. So these instruments are generally fixed, specifically fixed at a distance so as it represents human nose and human ear. So for example, I am here. This distance is identified as 500 millimeter here, right? So I'll just hold it here and record both the things, that while machining, what is the sound value, how it is changing, and I'll just switch on the air particle counter. It will also record that. So we could start the machining, and the data would be recorded in our LabVIEW software. Yeah, we can start now. So we have given 6 micrometer of depth of cut, and table speed here is 10 meter per minute. In this machine, we have like minimum, the minimum, that is its least count for depth of cut is 0.2. That is 2 micrometer here specifically. And the table speed here is, we have discrete table speeds available here. 2.5, 5, 10, 15, 20 and 25 meter per minute. So it is not a continuous. We cannot have, let me say, 2.6 meter per minute speed. So this is a conventional machine. This is not a CNC machine. So at this specific juncture, we have 5 meter per minute of speed, table speed. Now we'll start the machining. You will observe spark in the forward and backward stroke here. So what we did here, we did the machining. This is one machining pass has been done. Now, it was forward and backward stroke. You might have observed the spark that occurred during our machining here. So this actually the stroke that is taken into account for calculations is the forward stroke only, because that is very new stroke. Backward stroke is just taken for like some back-end calculations, that is it coming as, is the pattern similar or not. So you might have observed the values that were during the machining time were when the machine is on. This is average value. It was of the order of 80 to 85. When I'm speaking also, this value is coming. So this average value is not of the not of concern here. What is important is the peak value. When we reach the peak value, that may hinder in the long run to the operator here. So these two parameters are for controlling the work environment, that is the how it affects the human operator here. Right, we cannot just control, we just monitor this thing. Whatever we do machining remains within a specified specified levels which are recommended by various bodies. So this data is recorded in our machine in aerosol laser, and this is recorded here. This data would be used further for monitoring this one. Okay. I am on the interface, this LabVIEW software. See, we are running a second run here for the machining. So these are the two strokes available, the forward stroke and backward stroke. So these are the forces which have been obtained. So I will stop this here. Now, you see only two forces obtained here. This one is not changed. So this is our normal and tangential force. So we'll just obtain this data and I'll just save this somewhere. So as we have obtained two values here, two values of forces here, this will be further converted into specific energy, that is energy per unit volume of material removal, and that with respect to, and then we'll just find what is surface roughness. Now I'll just tell in the next sections that how we are just reading and cleaning the data, and how we just analyze the data to find final output. So what we have here is surface roughness tester. This is Mitutoyo SJ210 surface roughness tester. In this case, see that this screen is, the upper bar was red. Now it has turned to green. When we just touched this probe here with the workpiece surface, it has turned green. Now he has switched on. The probe is moving, and it is taking 5 samples. Here 5 samples into 5 written in the third row here. Point of 0.8 mm. So it has moved totally 0.8 into 5, 4 mm to 4 mm distance, and given total of average RA is this much. Also you have just have observed that it has given the graph as well here. So we are again doing one experiment to show the graph, how the graph is coming here. So it has moved 0.8 mm into 5, and this is RA coming 0.6 micrometer for one sample. And we do not only take RA once, we take it at multiple locations here, and on one location we might do a number of replicates so as to find that there are no noise levels here. So, for example, it is 0.6 micrometer here. So in different machining treatments, that are different depth of cut and speed combinations, we might observe different RA values and different force values as well. So those would be used to finalize our final setup, which gives best mix of these two. So this is used to find the surface roughness of this specific workpiece which you have machined here. The reason to do grinding is to have surface roughness only, good surface roughness only, whatever surface roughness is desired. So in this case, the resource parameter and quality parameter. In resource parameter, we can use force, energy, or certain other things which are input, the cutting fluid, and whatever resources inputs are there. In quality parameters, one can choose the parameters which gives us the quality of our workpiece of machining. For example, in this case, we have taken surface roughness as the parameter. So one can either choose the wear, tool wear, or wheel wear, etc. Those parameters come together. So this parameter will be taken here. So we have recorded this data. We have done multiple experiments before, and we'll just give you how to analyze the data and find the final output with respect to grain.